Fine, fine. How are you?
Very good.
That's great to hear. That's great to hear.
Thank
So
you.
guys, feel free to participate. The previous lesson that we had on Thursday, that was great participation, and that is nice. That is good. So each and every one of us should be free to participate, especially on the first part where we're going to be having a recap on what we looked at last time. It's good that we should participate. Participating enhances our understanding and our learning and retaining of things. So on the recap on last time's lesson, who remembers what we looked at in a nutshell? Anyone, guys, what did we look at on Thursday?
Cells the need of prokaryotic cells. Yeah.
Okay, those that were in my class. Remember, we had 2 classes. Then there are those that were in my class. What did we look at? We are looking at proteins. So there are certain things that we looked at with regards to proteins on Thursday. Guys, those that were there, what did we look at?
But I think we looked at the 3 types, which were primary, secondary, and tertiary. Right. Yeah.
Okay, thank you very much. Yes, we did look at those, the levels of structures, the levels of protein structures. So we looked at the primary, secondary, and tertiary. Before that, we looked at the formation of peptide bonds, the formation of peptide bonds. And we did say that peptide bond formation happens through the process of condensation. We said that this happens by the joining of monomers. So in this case, we are talking about amino acids, monomers forming the peptide bond. After looking at the peptide bonds, we then started looking at the levels of organizations that are found in proteins, the levels of organizations found in proteins. So on the primary structure, what did we say is the primary structure? What is the primary structure? Guys, come on, guys, don't disappoint me. What is the primary structure?
I think the sequence is just a sequence of peptides.
It's a sequence of amino acids. A sequence of amino acids, which are joined by the peptide bond. So the primary structure is simply the sequence of amino acids, just sequence of amino acids. And what's the importance of the primary structure? Guys, what's the importance of the primary structure? So one of the functions or the importance is that the primary structure is fundamental to its function, to a protein's function. What is the other one? As levels of protein structure, we said that the primary structure is also fundamental to the higher levels of protein structure. In short, it is fundamental to the secondary, tertiary, and quaternary protein levels. So it's very important, very important. Then we looked at the secondary structure. What did we say about the secondary structure, guys? Anything that you can remember on the secondary structure? Okay, so we said that the secondary structure is created in part by hydrogen bonding that occurs between the peptide bonded backbone. Remember that? And we said that this secondary structure actually distinctively shaped sections of proteins, which are stabilized largely by the hydrogen bonding. And this hydrogen bonding occurs between the oxygen on the carbonyl group. The oxygen on the carbonyl group. Remember, we said that when the peptide bond is formed, the carboxyl functional group of an amino acid is converted to a carbonyl. So this hydrogen bonding occurs between the oxygen on the carbonyl group, or the C, that is carbon double bonded to oxygen. So the oxygen on the carbonyl group of one amino acid residue, and the hydrogen on the nitrogen hydrogen groups of another. So guys, what did we say about the oxygen atom in the carbonyl group? What did we say? What did we say about the oxygen in the carbonyl group and the hydrogen in the NH group? What did we say on those two? Why is it that a hydrogen bond forms between these two? Between the oxygen on the carbonyl group and the hydrogen on the NH group? Guys, what can you remember?
Because of the different charges that are traveled for.
Okay, so we see that the oxygen in the carbonyl group has a partial negative charge because it has a high electronegativity. Well, when we look at the hydrogen, which is on the NH group, it has a partial positive charge because this hydrogen is bonded to a nitrogen atom, which has a high electronegativity. So no wonder there's a hydrogen bond forming between these two groups, or between these two atoms. And then we said that in most proteins, these polar groups can be aligned and they form hydrogen bonds with one another. And the backbone bends to form one or two possible structures. Which are those structures we mentioned? Which structures in secondary protein level, guys? As we said, there's alpha helix and beta pleated sheets, isn't it? Right?
Yes.
Yes. Are people able to get my see my screen?
Yes.
Okay, someone was saying that they are not able to see the screen.
So is it just showing the recap on last class session?
Yes, the screen should show recap on last time's lesson.
Okay.
Yes. So we said alpha helix and beta pleated sheet, isn't it? So that was on the secondary structure. Then on the tertiary structure, what are some of the interactions that we talked about? What are some of the interactions that occur in the tertiary structure? Guys, what are some of the forces that are found in the tertiary structure? We've forgotten. Anyone? So I said that there are 5 interactions. Said that there are 5 interactions that are involved in the tertiary structure. There are 5 interactions. We did mention that there's hydrogen bonding that occurs in the tertiary structure. That's one of the interactions that occur. We also mentioned that there are also hydrophobic interactions that occur. What are the other three? Any other that we mentioned?
The van der Waals interaction.
Thank you. Yes, the van der Waals interactions. Yes. Any other?
What of the disulfide bonds?
Yes, we mentioned about the disulfide bonds. Yes. What others? As the last one? As the bond that occurs between positive and negative ions. Yes, the ionic bonds, isn't it?
Yeah, the ionic.
Yeah, so those are 5. We've mentioned the 5. The disulfide bonds, where are they found? When are they formed? Which amino acid is critical to the formation of the disulfide bonds?
System? Is it system? Something
Thank
like
you.
that.
Yes, it is. So cysteine. It is cysteine, yes. Okay, so that's basically what we looked at last time. So we're going to continue from where we left off. After the tertiary structure, we have the quaternary structure. So look at the first 3 levels of protein structure. These involve individual polypeptides. However, we find that some proteins contain multiple polypeptides which interact to form a single structure. So this combination of polypeptides is what is called the proteins, or it's what gives the proteins a quaternary structure. So in short, the quaternary structure of a protein is the association of several protein subunits, several protein chains, association of several protein chains or subunits into a closely packed arrangement. So we find that each of these subunits, each of these individual subunits has its own primary, secondary, and also tertiary structure. Has its own primary, secondary, and tertiary structure. So in the simplest case, we have a protein with a quaternary structure, which can consist of 2 subunits. So it can consist of just 2 subunits that are identical. And when there are just 2 polypeptide subunits, we call such a structure or a protein a dimer. So di means 2. Di simply means 2. So as mentioned earlier, many of the functional proteins are actually composed of 2 or more polypeptide chains, which are able to interact in specific ways and hence form the biologically active molecule. So the quaternary structure is actually the resulting 3-dimensional 3D structure. So you find that in the quaternary structure, any alteration in the structure of the subunits or how they are associated can cause marked changes in the biological activity of the protein. So that's very important, as we are going to see some examples. We are going to see some examples. Now, the same types of interactions of forces which produce a secondary and tertiary structures also contribute to the quaternary structure. So the same interactions that we find in the tertiary and secondary structure are also, or rather contribute to the quaternary structure. They contribute to the quaternary structure. So I find that these subunits in the quaternary structure are held together by hydrogen bonds and also van der Waals forces between the non-polar side chains. So the hydrogen bonds and the van der Waals forces will hold these subunits between the non-polar side chains. So remember I said they're the same interaction. So it means that in the quaternary structure, we have the hydrogen bonds, we have ionic bonding, we have hydrophobic interactions taking place. Also have the disulfide bridges, and we have the van der Waals forces. So for example, when you look at a functional antibody or antibody, it consists of 4 polypeptide chains, which are joined by a disulfide bridge. So remember the disulfide bond. So a functional antibody will contain 4 polypeptides. So this antibody hence has the quaternary structure. And these disulfide bridges are actually a common feature of antibodies and also other proteins that are secreted from cells. So these help in the stabilization of the molecules in the extracellular environment. So they are very important. So an example of a molecule, the quaternary structure is the antibody. We have the molecule hemoglobin. Have you ever heard about hemoglobin?
Yes.
What have we heard about hemoglobin? What is it?
It helps in the diffusion of oxygen in the red blood cells.
It helps in the distribution of oxygen in the red blood cells. Okay. Another, what have we heard? So remember when we looked at the functions of proteins, we did mention that proteins there are proteins that act as transport molecules. And this is one typical example of a molecule which acts, a protein molecule which acts as a transport molecule. So it's a molecule responsible for the transportation of oxygen. It's an oxygen carrying molecule. It's an oxygen carrying molecule. So the hemoglobin, which is a protein in red blood cells, is responsible for oxygen transport. It is an example, the typical example of a globular protein with a quaternary structure. So it is a typical example of a molecule with a quaternary structure. Now this hemoglobin consists of 574 amino acids, which are arranged in 4 polypeptide chains. So we have 2 identical chains which are called the alpha chain, and also 2 identical chains which are called the beta chains or beta subunits. So it has 2 alpha chain subunits and 2 beta chain subunits. Now, when you look at each of these each alpha and each beta subunit will contain its own primary structure, which is going to consist of a specific sequence of amino acids. Remember, I said that the primary structure is this amino acid sequence, the amino acid sequence. And then after that, each subunit then will assume its secondary structure. So remember, it's primary, then secondary, primary, and then secondary. So they're going to assume a secondary structure, which is going to consist of alpha helixes and also beta sheets, which will then be arranged in a specific structure, in the tertiary structure. So primary, secondary, and tertiary. Primary, secondary, and tertiary. And then lastly, these subunits will then be arranged into their final quaternary structure, the quaternary structure, which is a final structure for this protein, final structure for this protein. we have other enzymes or other proteins which actually do not have the quaternary structure, which means that they end at the tertiary structure. So for example, enzymes such as a lysozyme, it has a tertiary structure as its final structure of the protein. So an example of a quaternary structure, we have given it hemoglobin. So this is the structure of hemoglobin. So remember, they have the beta chain, the alpha chain, the beta chain, the alpha chain. Remember, I said that it consists of 4 polypeptide chains, and each is joined to an ion-containing molecule, which is called heme. So the hemo, remember, it's hemoglobin. The hemo part comes from this ion-containing molecule, heme, and the globin part, hemoglobin. And then let's look at another protein, which is collagen. This is a picture of collagen. So this is collagen, representation of collagen. So you can see there are 3 polypeptides. We have this one, we have 2, and we have 3. So it consists of 3 long polypeptide chains. So this is collagen. So collagen is a fibrous protein. It's a fibrous protein. Its primary structure has a repeat sequence of 3 amino acids. That's glycine, proline, and any other amino acid. In its secondary structure and also tertiary structure, glycine and proline will allow the polypeptide chain to be wound into a tightly coiled straight left-handed helix. Find that in the tertiary structure, these 3 helical polypeptides are wound around each other and are held by hydrogen bonds and disulfide cross linkages, which leads to the formation of fibers. Now it is in the form of elongated fibrils, which form fibrous tissues. I find that collagen cannot be stretched, and for this reason, it is important for its connective function in tendons, cartilages, bone, the skin, the blood vessels, the digestive tract, and other tissues as well. So collagen is a fibrous protein, cannot be stretched, and it's important for its function. Hence, collagen functions as a structural protein. Remember, among the functions of the proteins, we said that there are enzymes. They can be classified as enzymes. We have structural proteins, we have storage proteins, we have transport proteins, we have regulatory proteins, such as protein hormones, for example, insulin, which we are going to look at. We also have motor proteins and also protective proteins. So we find that actually collagen is a structural protein. So when you look at the proteins, we find that some proteins actually have unusual amino acids. In addition to those common 20 amino acids that we talked about, we find that there are unusual amino acids which are contained in some proteins. So these rare amino acids are actually produced by certain modifications. So there are certain modifications that take place, leading to the production of these rare amino acids. So we find that these rare modified amino acids will form the structure or a component of the protein. So we find, for example, in the same molecule of collagen, we find that when these are actually incorporated into collagen, for example, lysine and proline, these are able to be converted into other molecules or other substances. So they can be converted to hydroxylysine and hydroxyproline. So now these molecules are going to lead to the formation of these links. They're going to be responsible for the formation of cross links that occurs between the peptide chains, which make up collagen. So now these cross links are the ones that produce the firmness and the great strength that collagen has. So collagen has great strength. Collagen has firmness, and this is produced by these cross links between the peptide chains, which are formed by the modified lysine and modified proline, which are hydroxylysine and hydroxyproline. So no wonder this collagen is important for its structural component or function in tendons and cartilage and the rest. So collagen has a fibrous type of quaternary structure which allows it to function as the major strengthening of animal tissues. It consists of 3 polypeptide chains wound about one another and bound by cross links between their amino acids, as we have mentioned already. Now this is a representation of insulin. Okay, so here's a question. You can unmute yourself to answer. What can you observe on this about the molecule of insulin? What can you observe? Let's look at the diagram. Guys, what can you observe?
Connection between the chains is at the size, is it cysteine? Yeah, cysteine.
Okay, so yes, so you have bonds between the chains, isn't it? What bonds are these? These that are formed between cysteine amino subunits. Guys,
Disulfide.
yes, you have the disulfide, isn't it? Disulfide bonds formed between the cysteine amino acid subunits. These subunits. So between cysteine and cysteine forming the disulfide bonds. What else? What else, guys? Guys, just look at the protein here, the structure. What can you observe? One of the observation here he has made is the presence of the disulfide bond between these two cysteine amino acid subunits. What else? Some of the labels are even given. We have chain A, isn't it? There are 2 chains. So there are 2 chains. We have this chain. Remember I mentioned that these chains are connected or joined by the sulfide bonds, the disulfide bond, which are formed due to the presence of the sulfhydryl functional group. So there are 2 chains. One chain has theta amino acid, right?
Yes.
Yes.
Yes, and the other chain has 21 amino acids. What else, if you can observe anything else? As do you know, have we ever heard of
Sir.
insulin? Yes.
Is it
Sorry?
that is it that chain B has its co group being attached to THR, the amino acid, and then chain A is its core group is being attached to another amino acid called ASN.
Oh, there and here. Okay, so
Yes.
you're saying the carboxyl group on chain B has threonine attached to it, and then for chain A it has ASN, and then for what about the other? The amino group here
is being attached to glycine.
Glycine, and this one
Phenylalanine.
Okay. Any other observation? Okay, so that's it, right? So look at this, the 3D, three-dimensional structure of insulin. It has two chains, as we have already observed, and find that these chains or this structure is stabilized or further stabilized by the disulfide bridges or bonds, which are forming between the cysteine residues. Remember, when the amino acids form chains, we call them residues to differentiate them from the monomers amino acids. So it's formed between the cysteine residues, formed between the cysteine residues. So those are some of the observations. You've actually made great observations. How many cysteine residues are in the insulin molecule?
3.
3, right? 3. Is that correct?
Is
Any
it
count
6?
answer? There are 6, right? Yeah,
There are
so 3
6.
on each. Yeah, 3 on each chain, right? So on one it forms 3 3 disulfide bridges. So there are 6 cysteines.
Sir, can you come again?
I asked that how many cysteine residues are there? So there are 6, right? There's 1, 2. Which other one? 3, 4, 5, and 6. So there are 6. So no wonder we have 3 disulfide links or bridges. Now, what is the function of insulin? I'm sure you've heard insulin before, right? Which people uses insulin that you've heard of?
People that have diabetes.
Okay, so people that have diabetes. So that is they are able to use insulin, right? So this is, but however, this is the biological molecule insulin. So at least we've heard.
So is it only people that have diabetes that use insulin, or it's like everyone?
No, everyone has insulin in there. Normally, everyone have insulin in their body, but understand his answer is coming from the perspective of someone with diabetes who receive insulin. Yeah, but otherwise, everyone have insulin in their body. Normally, everyone must have insulin. So you find that insulin, remember when we talked about the functions of proteins, there's a regulation. There is a regulation. So insulin function to regulate the amount of glucose in the blood. So you find that when there's too much glucose in the blood, insulin will promote synthesis of glycogen. And then this glycogen is then going to be stored in the liver and muscles. Remember, one of the functions of the carbohydrate is storage. They act as storage molecules. So insulin is responsible for that. So before you continue, because it's already 40 minutes, you can just log out and log in back so that we finish up.